Okay, so we've previously looked at this problem and we've turned it into its components, its internal force components at plane AA, using the method of really just translation and the effects caused by the component forces that are applied at the end. I recognize that not everybody sees in three dimensions as well as others. And so I wanted to look at an alternative way to do this. And we'll use a very classic partial free body diagram. But to assist us, we're also going to break this down into three planar views. So really a front view, a top view, and an end view, if you want to think of it that way, or the ZY plane, the XY plane, and the ZX plane. And I've drawn those out here to try to help us see what these various component forces are going to do at our plane. And so let's look at them. First off, we have our front view, if you want to call it that, our YZ plane. And so if we look up, it goes up 200 millimeters along the z-axis and then out the arm of 400 millimeters. And really the only force we can see in this plane is the 1,000 newtons going in the positive y direction. And then on the XY plane, or the top view, of course, it's coming up in the kind of that Z direction, which we don't see. And then we have that arm going out 400 millimeters in the Y direction. And in this case, we can see both forces, the 1,000 newtons continuing in the Y direction and the 1,500 newtons at the end going off in the X direction. And finally, we have the end view. And so it's going up the 200 millimeters and then out, which we don't really see the out part. And we can only see the one component force of the 1,500 newtons going off again in the X direction. And so all of this is just a representation in the three views of our partial free body diagram, which we have drawn below the actual picture of the problem or statement of the problem down below. And what we want to do is we're going to look at, basically we're going to do our statics. We're going to look for the internal component reactions at our plane AA from each of these forces. And we're going to use a combination of our 2D views and our 3D view to kind of record them and see how they interplay. So the first one I'm going to do is I'm going to start, and I'm actually going to walk through kind of the 2D views and bounce back and forth between that and the 3D view, and hopefully that's going to make a little bit of sense and go from there. So we're going to start with the 1,000 newtons on the front view, and of course if we do or balance our forces, some of the forces in the Y direction, we know that down here on our plane, we're going to have a translation force. That's our force in the Y direction as a result of that 1,000 newtons. And when we sum it up, and we'll do the math at the end, but when we sum it up, we're going to see that that's equal to the 1,000 newtons. Now, if we do our sum of the moments about the origin, or about plane AA, if you will, we also see that we need to have a moment, and I'm just going to draw it in here as our moment, and it's about the x-axis to counteract that 1,000 newtons multiplied by its moment arm of 200 millimeters there. Now, so I'm going to put these down on my 3D view, and so we have our F at Y. Oops. We have our F at Y, and so here, and we have our moment in the X direction, and that's being drawn in our positive X as per our 3D view down here. So I'll put that in here. We have our M at X. So now that's all of the internal forces being caused by the 1,000 newtons as we see it in the front view. So let's go down to the top view. Now we see our 1,000 newtons, but we've already taken care of the translation from it, so we don't want to do it again. We don't want to add multiple images of the same thing, so we only want to get one of the components So having already done that, we're not going to do that. We're going to look again at our 1500 newtons. And so if we do our sum of the forces in the x direction, we see we're going to have a translation down here, a force in the x. And that force multiplied by its perpendicular distance also gives us a bending moment about the z-axis. And so to draw that in, to counteract the force, we're going to have our moment about the z-axis. And so let's put those down on our 3D diagrams. We have a force in the x direction. And I'll just draw it on this side over here. So we have our F at x and our m at z then. Moment about z, using our right-hand rule, it's going to be in the negative z direction. So there's our m at z. And then let's go down to the end view, and we see we have, again, we've already taken care of the translation in the previous view, so we don't want to do it again. But there's one moment that we haven't taken account of, and that's this 1500 newtons bending about the y-axis. And so we would have a moment in the y-axis like that, and so that would be drawn out here. Moment about the y-axis. Sorry, it's a moment, so we have to have the second arrowhead. And that would be all of our components of force. And we can hopefully use a combination of the two-dimensional view, which helps us see both the perpendicular distance and the moment effect that it's going to have. Now, one thing I would want to note is that all of these are on what we would normally call a negative face. And so we're going to have to do the equal and opposite to translate these over to the positive face. And that way it would match up with the method that we did previously when we were looking at the effects in 3D. So the only thing left to do in this one would be simply to do the math. Obviously we have our F at y, and this is where the 2D views are really kind of useful. So that's going to be equal to 1,000 newtons. I drew these all in so that they would be positive as drawn. And we're going to have an F at x, and that's the 1,500 newtons. And then we have our three moments. So let's just do them out here. So moment at x is equal to our 1,000 newtons, and that is multiplied by the 200 millimeter distance, and so that would give us a value of 200,000 Newton millimeters. And our m at y then would be equal to our 1,500 newtons, and that is also multiplied by the 200 millimeter distance to give us a value of 300,000 Newton millimeters. And finally, our m at z would be equal to our 1,500 newtons, but that's multiplied by the 400 millimeters to give us a value of 600,000 Newton millimeters. So again, if you wanted these values on the positive face to do your stress analysis, would you simply do the equal opposite, so same magnitude, opposite direction, put them on the positive face and carry on with our stress analysis. So hopefully this is useful between this and the other method that I did to help you in your particular manner of visualization to be able to see how we can get a 3D problem down into its force components, internal force components at a particular point or plane. So hope that was helpful, and we'll see you on the next one. Thanks very much.